I welcome you all for this presentation. In this presentation, we are going to discuss about Introduction to Algorithms, the second part of our course. Our course is Data Structures and Algorithms. Already we discussed about, we introduced the data structures. Now we are going to discuss about Introduction to Algorithms. So this is the overview of this presentation. We will be discussing about the definition of algorithm, then structure of an algorithm, then properties of an algorithm, then algorithm analysis and complexity, followed by summary of this presentation. What is an algorithm? We know that algorithm means it is a step-by-step procedure to solve any problem. Here you may see that the finite sequence, algorithm is a finite sequence of instructions. This finite is very important. Finite sequence of instructions, each of which has a clear meaning and can be performed with a finite amount of effort in a finite length of time. All are finite. So always the algorithm must quit or terminate. It won't run infinitely. So always there may be some finite steps. It must be countable. So a finite sequence of instructions, each of which has a clear meaning. Each and every step must have a clear meaning. So always we have to write efficient algorithm. That is very important, right? Anyone can write any algorithm. But whether the algorithm is efficient enough, it reduces the complexity, all those things we have to take care. So the finite is very important here. And how this term algorithm is coined means it originated from the Arabic word algorithm, which is linked in the name of the Arabic mathematician Muhammad al-Khwarizmi. So this Muhammad al-Khwarizmi is considered to be the first algorithm designer for adding numbers. So he is the first algorithmic designer. So only I have taken his for picture and I have given here for your reference. So how they coined the name. So if you are also coming up with any new proposal or new algorithm, how we have to coin the name. So we may get some idea. For that only I have given for the inspiration. Next, coming to the structure of an algorithm, all algorithm must have an input and the output. So we are giving an input and finally we need some output. In between we are having some steps like assignment step is there, decision step is there, repetitive step is also there. So this one or two steps we can have or we may not have, but input and output and only one intermediate step is important. So this is the structure of any algorithm. So while writing the algorithm, we have to keep these things in mind. Next is the properties of an algorithm. Finiteness, we already know what is a finite. In the algorithm definition itself we have seen. So always the algorithm must terminate after finite number of steps. That is very important. It can't be running infinitely. So always it has to terminate. So we must have some finite number of steps. Next is definiteness. The steps of the algorithm must be precisely defined. Then generality, that is algorithm must be generic enough to solve all problems of a particular class. So always don't write for the particular input. That is very important. While writing the algorithm, you have to generalize the algorithm. So whatever the input given for that particular class, it has to work. Don't write for a specific input. It must be generic enough. Algorithm must be generic enough. That is very important. Next is effectiveness. The operation of the algorithm must be basic enough to be put down on a pencil and paper. So if you want to solve it manually means also it must work. Like that we have to design some algorithms. Next, input output. The algorithm must have certain initial and precise inputs and outputs that may be generated both at its intermediate and final steps. So if you want to display the output in between means also it is possible with the help of the algorithm. So while writing the program also, if you want to see what is the intermediate result, you can in between you can write cout or a print statement you can give and you can view the results as well. So the output may be intermediate result or the final result is also there. So this is these are the properties of any algorithm. Next is the main important thing, algorithm analysis and complexity. So now only we are entering into our new syllabus. Here we are analyzing the performance of the algorithm based on two scales. One is time and another one is space. So based on that we can tell that we have to compute the time complexity, then space complexity. Likewise, we have to compute. Any algorithm is there means we can compute these complexities and we can come to a conclusion that which algorithm is best. So if I am giving you one problem, so all these 61 members will be solving without looking or discussing with others, means each one of you is coming up with a very new algorithm, right? So totally we are having 61 algorithm for a given problem. So, but I have to analyze which algorithm is best. So, in terms of time complexity and space complexity, I have to analyze and I have to choose which algorithm is the best algorithm. So, for that only we are having the time complexity and the space complexity. So, the time complexity of an algorithm or a program is a function of the running time of the algorithm or a program. So, mainly it is based on the running time of any program only. We are computing the time complexity. Then space complexity is how many space or how much memory location is required to store the particular algorithm up to the completion, because in between some intermediate results are coming means we have to store it. So all those things we have to analyze with respect to the space, that is the space complexity. The time complexity of an algorithm can be computed using the empirical or posteriori testing, then theoretical or a priori approach. So what is empirical or posteriori testing? Mainly this approach calls for implementing the complete algorithm. So empirical, posteriori, previous, the meaning. So we are just calling for implementing the complete algorithm and we are executing them on a computer for different instances of a problem. That is the empirical or numerical computation or empirical or posteriori testing of the algorithm for finding the time complexity of the algorithm. Next method is theoretical or a priori approach. It mainly calls for the mathematically determining the resources such as the time and space needed by the algorithm. Mainly it is given as a function of parameter related to the instances of the problem. This way only we are calculating or we are computing the complexity of any algorithm. These two approaches we can follow to compute the complexity of the algorithm. So this a priori, let us see some example related to the a priori analysis. This a priori analysis computes the efficiency of the program as a function of the total frequency count. Here total frequency count plays a vital role. So based on the frequency count, we can find out the complexity of any particular program. So here one example I have given you, that is estimate the frequency count of the statement x equal to x plus 2 occurring in the following three program segments A, B and C. Just the statement is coming in all the three program segments, but different loops are involved, some symbol thing is there, likewise some difference is there. First is the program segment A. Here some lines are there, that means we are entering the input, some lines are there. So in between we are getting x equal to x plus 2. For this particular statement, if you count the frequency, means here we are getting only one time only it gets executed. So the frequency count is 1. So the total frequency count of this particular segment is 1. So it is given as time complexity of the program segment A is order of 1. This O, it is called as big O notation. It is we call it as asymptotic notation. In the next presentation we will be discussing about asymptotic notation only. Here it is called as big O, order of 1. So because it the frequency count is 1. For the segment B, you may have seen that here we are having one for loop. So this for loop is 1 to n. So anyway, we will be entering inside the for loop n times. So after n, we will again we will check whether the condition is satisfied or not. At that time, we are going to execute once. So only here the frequency count is n plus 1. So this for loop, it is n plus 1. So once we enter inside the for loop, this statement will be executed n times, n statement will be executed n times. So totally the frequency count is n, 1, 2, 3. So 3 n's are there plus 1 is there. Always this small numerical numbers, numerals are negligible, very small, so it is negligible. So we have to write the time complexity of this particular segment is order of n. Whichever is maximum, that we have to write order of n. So these constants are negligible, very small number. So don't want to consider these things. We are just writing order of n. So for a single for loop, it is a order of n. Coming to the program segment C, here we are having two loops. So J loop is there, K loop is there, two loops are there. So we know that for this for loop, n times we are entering inside. Finally, again we are checking. So it is n plus 1. It is n plus 1. Then this for loop also n plus 1 only. But this K loop is next to or inside the J loop. So again n times. So n plus 1 into n times. So this x equal to x plus 2, it is coming inside 2 for loop. So n into n, that is n square. This n statement is for this k for loop. So it is n square. This n statement is for the j for loop. So it is n. So here if you think n plus 1 into n is n square plus n, right? So how many n square are there? 1, 2 and 3. So 3n square. How many n's are there? 1, 2, 3. 3 n's are there. How many constants are there? Only 1. So 1. So 3n square plus 3n plus 1. We are counting the frequency. So here which is the maximum value? N square only. So it is order of n square. All the constants we have to consider it as a negligible, very small thing. N is only very much important, and if you have a huge number of records, the n value is very large, right? And comparing n square and n is only greater, n square is greater than n. So always the higher part we have to consider for this complexity analysis. So order of n square we have to write. This is one symbol. These are some simple examples to compute the time complexity of any algorithm. I think you might have understand this. And in the next presentation, we will be discussing about the asymptotic notation. There we can see different methods of finding the time complexity of the program. So in this presentation, we discussed about what is an algorithm, then the structure of any algorithm, then properties of the algorithm, and we discussed the need for algorithm analysis and complexity, and what is the need for time complexity, space complexity. Then we have seen some examples also to compute the time complexity of the program segment. In the next presentation, we will be discussing about asymptotic notation. Thank you.